Hello students, this is lesson U5A03a. By the end of the lesson, you should be able to say, I can derive the similarity proportion of right triangles. And just to be specific here, we have been doing this for the past couple lessons. However, this is for a very specific kind of right triangle setup. So let's take a look at what I mean. So in this case right here, this is the setup, and you're going to see this in various types of like Regents questions, SAT questions, and this is not to say that the Regents and the SAT are designing questions just to torture you. However, this kind of setup comes up all the time in engineering applications, in scientific applications, which is why it is important to recognize this. Okay, so what we have here is actually three overlapping right triangles. And if you can take a look at this, right, I encourage you to write out what triangles exist in this diagram, okay? Starting with the smallest right triangle, moving on to the second biggest, moving on to the largest right triangle. I encourage you to try and do this. Please take a moment and do that. Hopefully you had some time to think about this. So the three right triangles end up being this, and this should be triangle symbols here. So I have three different right triangles. I have triangle ADB, and then I have triangle DBC, and then I have triangle ADC. I hope you guys can also recognize, right, that with these right triangles that are drawn right now, that we've listed out right here, notice that angle C is different from angle A, right? And it should also be recognized that that the other angles over here, okay, are actually going to be the same angle measures. So whatever this angle measure over here is, okay, I know that the other angle over here should be congruent to the angle over here, okay? And this angle over here, angle ADB, should be the same as angle C. Why is this the case? Well, this is the case because, let's just think about it. If the angle over here, let's say was 30, the angle over here, therefore, must be 60, yeah? So that means the angle over here must be 30, and the angle over here must be 60. This is not by coincidence. Let's try that again. I'm going to erase all these. Let's try that one more time. Let's say if this was, let's say 20, the other angle over here should be 70. And then this angle over here should be 20, and the other here, and the angle over here should be 70. So you can see clearly whatever number we throw in, okay, we're going to see these numbers repeat itself over and over and over, okay? So we have this angle that had one tick mark, okay? There should be one tick mark over here, and the other angle over here should have two tick marks, okay? Which is, again, reaffirming why we have three similar right triangles happening. So recognizing this, that we have three similar right triangles, what I want you to do next is I want you to actually draw out these three similar right triangles the same manner that I have here. Now that we have this, okay, what we're going to try and do is we're going to compare, okay, various side lengths, okay? And what we're going to do is we're going to compare the shorter leg between two triangles at a time first, and then compare the longer leg, and then compare the hypotenuse. So what's the setup then? Okay, so let's say if I compare the shorter leg first, I recognize that, and I'm comparing it between these two triangles first, okay? So I recognize that AB to DB, again, shorter leg, right, the shorter leg. Because all three of these are similar, I immediately recognize that between these two triangles, okay, it's going to share the same proportion. This must be true. DB to AD. All right, so now with the same approach, okay, I'm going to compare the longer leg to between each of these triangles. So I'm going to first start off with these two triangles, okay? So again, I'm comparing the longer leg now. So I'm going to have DB to CB is proportional to CB to CD or DC, whichever way you want to call it. Doesn't matter, right? And then we are going to compare the hypotenuse. So I have AD to DC. Again, this is between these two triangles, right? Is going to be proportional to, again, the hypotenuse being compared in those two triangles. And that is DC to AC. And actually, I am going to be consistent in the way I'm calling this. I'm going to call this DC. And yeah, that's it. Okay, so this is actually going to be the proportionality constants. Okay, so one more time, when looking at this, okay, another way of looking at these three proportions set up. We finished this already. I just went through it. Another way of looking at it is, okay, I can compare ratio of longer leg to the shorter leg. Again, I can compare the longer leg to the shorter leg. If I do this, I can do AB to DB is equal to DB to BC. That proportion is going to hold true. I can also compare the shorter leg to the hypotenuse, which is AC to AD to AB. And I can also compare the longer leg to the hypotenuse, AC to DC, as well as DC to BC. Again, I encourage you to pause the video and to really try and digest these proportions, okay? And you should be able to recreate these proportions on your own, like on the spot. It's not like I sit there and try to memorize these things, these facts. If you look at this, compare, I mean, just looking at these three things, right, compared to these three things, it's really daunting. It's like a lot of information to take in. It's a lot of information to digest, right? So I don't encourage you to try to memorize this, not at all, okay? And instead, I encourage you to be able to recreate this, okay, when the time comes. Now, with that said, there is one formula that comes in super handy, okay? That comes up all the time in different regions questions, as well as ICT questions, as well as in many different engineering applications. And what is that? So it's this thing right here. I want to show you to right here in this diagram. Okay. So as it turns out, okay, we recognize that the shorter leg, okay, which is AB here, right, divided by DB is going to equal to, and so again, I'm comparing the smallest triangle to the mid-sized triangle. So the mid-sized triangle, the shorter leg, is going to be DB to BC. Okay, so this proportion here comes up all the time, and this is what I encourage you to memorize. Not quite this formula exactly, but this setup right here. Actually, I didn't mean to erase that. So let's say if I call this length, okay, this length right here, M, and this length right here, L. This length over here is going to be N, right? So what's the relationship? Well, L times M will equal to N squared. This is the relationship. Can you see how we can get to this equation from that proportion there? So again, AB is M, yeah? And DB is N. And DB is N, and BC is L. If I cross multiply, isn't that what I'll end up with? L times M is equal to N squared. And again, so this comes up all the time in various different types of like algebraic applications and geometric applications and engineering applications, which is why I'm trying to bring it up right now. And there's a name for this formula. This is actually referred to as N squared is we call this the geometric mean. call this a geometric mean of L and M. Why is it called a geometric mean? This actually is not the appropriate place to talk about this. There's a lot involved, but for the moment, okay, let's just understand that this formula is referred to as the geometric mean, okay, of the hypotenuse that's been proportioned. Okay, so this formula comes in super handy. You are going to be using this in the next lesson and next assignment.